Okay, so today's one of my favorite lectures on color. We'll see how it goes because there is some conflict between the things I will show today and the brightness of the illumination required for the videoing, but we'll see. All right, so what we're going to do is, as we've done several times in the course, we'll start with theory, and that'll be mostly today, and then on Wednesday we'll talk about practical applications of color. So we'll start with spectral power distributions, color responses, which mean our three receptor systems. We'll talk about the 3D color space. So if you prefer a geometric interpretation to an algebraic, this should appeal to you. We'll talk about reproducing colors. Those are the trichromatic matching functions. And then we'll talk about this question you've had since nursery school of what are the three primaries. Red, green, blue, cyan, magenta, yellow, red, blue, yellow. We'll talk about non-rectangle, non-Cartesian systems, cylindrical and polar systems, and then we'll talk about chromaticity diagrams, which will lead into two practical applications for photography. The first one's white balancing, and the second one is standardized color spaces and gamut mapping. Where is my... Okay, so let's get started. And we'll probably only get to this today. We'll finish on Wednesday. Okay, so start with a famous scientist, as I often do. We'll start with Newton. And so here is his experimentum crucis, where what he did was he divided sunlight into colors using a prism, and then showed that these colors, so he then selected out one color and put it through another prism and showed that it could not be further subdivided, that there was something fundamental about what was happening in that first prism. Actually, to me, his more telling experiment is a second one he did. This, by the way, is his original drawing, for which there's no original drawing by him, but here's the experiment. Very clever. He took a prism, split the colors, ran them through a convex lens, which recombined them, and then found that this beam was identical in all properties that he could measure to the original beam. In particular, he could redivide them again. And so from this, he concluded that sunlight was composed of these individual colors that could be separated using a prism. Very, very clever experiment. So, of course, we know now that there's this electromagnetic spectrum from long radio waves all the way to X-rays here, and that the visible spectrum is only a small part of it, between 400 and 700 nanometers of wavelength. And it makes the rainbow. And we can talk about the spectral power distributions of light sources. So tungsten might look like this. It's particularly heavy in the warm colors, the reddish colors, the high nanometers, like 700 or 800. Daylight is fairly uniform. Mercury fluorescent is kind of spiky. There's a low pressure sodium, which is just kind of a single spike. High pressure is a bit better. And then here are some of the metal halides, which includes a mercury vapor lamp. So the units here are watts, joules per second. All right. So what's important to us as photographers about this is what happens when this light interacts with objects. And so the way to think about that is you take the spectrum of the illumination and you multiply it at each wavelength by the reflectance of the object. And that yields the stimulus that enters your eye, because it's this sort of situation. The cause is absorption by the material, although there are some materials with more exotic properties. Transmittance works the same way. So you would have an illumination and then you would have a transmittance spectrum. So it would be a percent transmitted at each wavelength. And you would multiply the two and you would get the same thing. So this fact that you're multiplying these two spectra is why some things look weird under some lights. And so for me, my favorite example is under a sodium vapor light, my maroon van turns completely black, or very, very dark gray. I cannot see its color at all, because where it reflects in the spectrum, and where the sodium vapor light has its spike are disjoint. They're not in the same place. So when you multiply them, you just get basically zeros across the visible wavelengths. Okay, so this is all fairly straightforward. Here are some reflectance spectra for common objects. So what's interesting here is this is labeled on this diagram as a white petal. I guess it's this yellow plot here. And this is labeled as a white flower. And so they're both labeled white, although they clearly have different reflectance spectra. So Newton observed this. He could split colors using his prism, and he could block out some of them, and he would get maybe left over a red and a green and a blue and block some of the others. And then he would recombine them using that arrangement that I showed before, and it looked to him the same as the original sunlight, although he could verify that it was not the original sunlight because he could resplit it and see that it had some of those colors missing. So this notion that different spectra may appear the same are called metamers. He could not explain this, which is the right answer for him. He didn't have the mechanism to explain it, so it was brave of him to say, I don't know what this is caused by, but they look the same to him. So two reflectance spectra that match are metamers under one illumination may not match under another, so clothes that match in the store may not match outdoors. Got to be careful about that. So, any questions on reflected spectra? So we haven't introduced the human visual system at all yet. But I just want to make sure that we're clear on the reflectance spectra and the fact that you multiply the illumination by the reflectance. Something on the dory. Okay, this is pretty straightforward so far. We haven't really gotten to the fancy stuff yet. Okay, so let's talk about the color response in animals and humans. All right, so let's talk first about a horseshoe crab. So here's wavelength, and here is response. We could call this retinal absorption if we like. So that we make sure that we understand it's very early in the visual system, just the absorption of light by pigments in the retina. And this is not necessarily what a horseshoe crab looks like, but it's probably not too far away. So those are in nanometers. So how many colors does this horseshoe crab see? A black and white crab? Well, it looks like it has response all across the visible spectrum. Why? What do you mean it's black and white? You're saying it only sees one color?
It sees intensity with that distribution.
Okay, Zalman knows too much. So he's right, though. The way to think about it is that the horseshoe crab can, of course, see many colors in the rainbow, but cannot discriminate them, in the sense that it cannot distinguish changes in intensity from changes in illumination. So, of course, some of the responses, like this wavelength versus this wavelength, so lambda 1 versus lambda 2, it cannot distinguish at all. They will have the same response. But more interestingly, it cannot distinguish a unit amount of either of those two wavelengths from half as much of lambda 3. Half as bright a light of lambda 3. It will get the same response for half as much lambda 3 as it does for a unit amount of lambda 1. And so it cannot discriminate a change in brightness from a change in wavelength. And that is the definition of color vision. Okay? So we say that the horseshoe crab then is a monochromat. That's the technical term for an animal that cannot make that distinction. All right, so let's go on to animals that have two receptor systems instead of one. So let's say we're designing a dog. We're present at the creation, and so here's one proposed dog. And we'll say that this curve here will feed receptor system A, and this one will feed B. So in other words, they will lead to different nervous pathways to the brain. How many colors does this dog see? Someone besides Zalman? Those are two receptor channels split here.
It's not very good because you get strong A, strong B, but you don't get gradations of partial A and partial B, which might give you additional color signals. So they're sort of pretty separated from each other.
They're separated. You don't get mixtures of A and B. So indeed, this dog will see exactly two colors. It will either excite A or excite B, and again, within each range, it won't be able to discriminate between a change in brightness and a change in wavelength. All right, so and creation was 6 days long, so we've got some time here before the ship date. Let's try again. How about this? And let's say that this is receptor system A, and this is B. How many colors does this dog see? Florian?
So within the range where A and B overlap, there's a continuous range of colors, but outside the overlap, you still have only the two colors.
Exactly. So within that range, there are mixtures. And for, let's say, wavelength 1, there may be this much A and this much B, and that ratio is unique. It occurs nowhere else in the visible spectrum. And so the animal can distinguish that that is lambda A. And the same thing here, it's the flipped ratio, and so the dog can distinguish that that's lambda B. But outside of this range, like here or here, it cannot discriminate for the same reason that we've talked about all along. All right, still got 4 days left in creation, so there's still plenty of time. Let's try again. How about this dog? So this feeds A, and this feeds B. How many colors does this dog see? How many? A lot. What's a color? Yeah. We'll get to that later. But according to my definition, it can see an infinite number of colors, as it really could see here, but over the entire spectrum from 400 to 700. In other words, at any wavelength in that visible range, it can discriminate a change in brightness from a change in color. So that's...
Sorry, for a single wavelength?
Yes, this is for a single wavelength. We're not talking yet about mixtures of wavelengths. All right, so the human, so this is a pretty good dog now. And a dog is a dichromat. So let's talk about humans. So a human, can you all still see this down here? A human is a trichromat. And we have something like this. And just to make these curves a little bit easier to see, I'll draw them in colors that kind of suggest their placement in the spectrum. And give them names. So the names rho, gamma, and beta kind of suggest red, green, and blue, but don't exactly mean red, green, and blue. They mean exactly what I've drawn on the graph here, that they are more selective toward the reddish, what we call the reddish part of the rainbow, versus the bluish part of the rainbow. And they overlap, all three of them overlap over pretty much this whole visible spectrum from 400 to 700 nanometers. So, do we see more colors than a dog? A bigger infinity? Okay. I haven't given you enough information to really understand the answer to that question yet. The answer is yes, but we cannot do any better job of discriminating a single wavelength. A dog can do that. If a dog looks at a rainbow and sees the same discrimination of color that we see when we look at a rainbow. So for single wavelengths, we both have full discrimination over the entire visible spectrum. But we can see more mixtures. We'll get to that a little bit later. Before we do, let's just think about some of the properties of what I've already drawn. So in particular, if I stimulate this human system with a unit amount of lambda 1, and this means what we read off of that chart of retinal absorption, and it responds with rho 1, gamma 1, and beta 1. And we stimulate the system, so that could be, for example, right here, there's lambda 1, and we can just read that right off of those graphs. And lambda 2 yields rho 2, gamma 2, beta 2. Then, and let's say that's over here, here's lambda 2. If we now stimulate the system with a single source that has both of those wavelengths, so I hesitate to write lambda 1 plus lambda 2. So let me just write and, because I don't mean that I'm going to add lambda 1 to lambda 2. We're not adding wavelengths. We're stimulating with both of those together. Then the result will be rho 1 plus rho 2, gamma 1 plus gamma 2, beta 1 plus beta 2. So there I do mean plus. The retinal absorption will be the sum of the retinal absorptions of each one of them, which is to say that at this level at least, the human visual system is obeying superposition. Okay? It is also true that if I stimulate it with a brighter amount of lambda 1, which I will indicate like that, let's say twice as much lambda 1 for n equals 2, then I will get n rho 1, n gamma 1, n beta 1, at least at this level of retinal absorption, before we've gone further into the visual system, which becomes different. And so this means that the human visual system, at least at the retinal absorption level, obeys scaling. So if a system obeys superposition and it obeys scaling, then it is a linear system, right? At least at this level. And the fact that it is linear lets us do all kinds of nice analyses and make all kinds of cool geometric diagrams, which we'll do momentarily. Okay, let's summarize what I've just said. If you have a stimulus arriving, so this is a spectrum. This is an illumination multiplied by a reflectance spectrum, which leads to a spectral power distribution entering the eye. What we do is we multiply at each wavelength times the spectral sensitivity. So this is a slightly different drawing than the one on the whiteboard at the bottom. It's slightly sort of iconified, and it's also normalized so that each of them are full unit height. Otherwise, it ought to look like this. And then that yields a response of that receptor system to each wavelength, making another plot. And then you integrate. You integrate across all wavelengths to get the total row response. And you can do that wavelength by wavelength multiplication followed by integration because of this property of linearity. And the same for gamma and beta. And the output is just 3 numbers. That is the total response in a 3-dimensional coordinate system, at least at this level of retinal absorption. Or if you prefer, we can do this algebraically. Same figure here. The stimulus has this funny international symbolism, LE. The E changes to other things if it has already gone through the human visual system and been scaled by it. We'll talk about some of these symbols later in the course when we talk about lighting and illumination. So the response to rho is then at each wavelength multiply that stimulus by the rho function, by the gamma function, by the beta function, and then integrate. So this is just in symbols what I just said in words. And that yields 3 numbers. Okay? Are people completely clear on that? Because it's going to get more complicated. Yeah?
So, can the combination of 2 wavelengths give you the exact same 3 numbers as a single wavelength?
Can the combination of 2 wavelengths give you the same
Let's lambda
numbers?
3. Can there be a lambda 3 that gives you the exact same response?
Could there be multiple combinations of 3 of them that give you the same response? Well, let's see. So what you're saying is, can there be spectra that when you plug it through all this will yield the same response? The answer is absolutely yes. And those are called metamers. So we still have metamers. There are an infinite number of those possible confusions of spectral power distributions that yield the same set of 3 numbers. Okay? So, another question.
Yeah. Is it done by experiments to show that human visual system is scalable and superposition?
Is it done by experiments? I'm not sure I know the answer to that. So the retinal absorption is something that can be easily experimentally verified because we're just looking at the absorption by a dye. You don't even need a live animal for that. Where the theory of 3 receptor systems came from is from a psychophysical experiment called the matching experiment, which I will show you here in just a few minutes. But this later data is from retinal absorption, which could be done in a wet lab. Good question. All right, there's a Dory question as well. What would the evolutionary advantage be of the particular wavelengths in the visible spectrum? It seems like we could equally be able to get value out of seeing in ultraviolet or infrared, so why don't we? Lots of animals do. Bees are very good at ultraviolet, so that they can distinguish the flowers that they need to pollinate. As to why we don't see radio waves, I don't have an answer for that. But there are lots of animals that do see a little bit further than we do in the spectrum. Florian.
As the wavelength goes down, as you go far into the infrared, it becomes more and more difficult to trigger chemical reactions.
Now, Florian's saying that as you go down into the infrared, it becomes harder to trigger chemical reactions. And indeed, a laser light or something that's further into the red will penetrate further into skin. And so it simply becomes hard to design a visual system.
And too far into the ultraviolet, the atmosphere is opaque. There's sunlight.
Too far, right, I should have known the answers to these. Right, too far into the ultraviolet, the atmosphere is opaque. And so these are actually convenient wavelengths because they are, the light gets through the atmosphere it is reflected by things, and it can be absorbed and sensed by a biological vision system. So there are good reasons for those rough limits. Great. Okay. So if you prefer a geometric interpretation, let's make one. And so I've got this great set of applets. So we don't need that one anymore. All right. So let me start a little bit more gently. Let's take these three axes. Let's take as three axes the three receptor systems that we just talked about: rho, gamma, and beta. And if we were to take a particular lambda, we could look up on these curves what its rho, gamma, and beta numbers are and use them as coordinates in this three-dimensional system. So that would mean going a certain distance out along rho, a certain distance out along beta, and a certain distance up, out in gamma, and a certain distance up in beta, and that would make a spot. We could do that all along this spectrum, and we would end up with a curve. So it's a little bit hard for me to draw the curve on a flat diagram. I'll show you the applet in just a moment. And so every single point along here is one point on this curve. And so this is called the locus of spectral colors. So it is three-dimensional, and here it is. So here's rho, here's gamma, and here's beta. And we can talk about the different parts of the rainbow. They each represent, you can see the tick marks here, these are the spectral sensitivity curves. And here are the points. So we can think about these as the coordinate curves of a parametric representation of a single three-space curve, if you would prefer. And here is that three-space curve. Okay. So we can play some games here. So let's see. If the response to one particular wavelength is, let's say, here, so that's kind of a orangey, and the response to another pure wavelength is, let's say, here, so that's kind of a green, what will be the response to a 50-50 mixture of those two wavelengths? Let's say a 50-50 mixture so that the total brightness remains the same. So where's it going to be here? It'll be here? No. It'll be right between them. Linearity, right? It'll be right here. Okay? Suppose we had three. You see where I'm headed here, obviously. So an admixture of three such pure wavelengths whose sum totals 1 will then be where? The triangle. That surface. If we allow the admixture to be of total brightness 1 or less, then what will it be? The tetrahedra that includes the origin, right? That's a more complicated shape there. we're beginning to talk now about a primary system, where I've arbitrarily chosen these 3 points as primaries. Suppose I chose a fourth. Let's put the fourth over here. That looks like it'll kind of do this, doesn't it? And it looks like there are colors that I can reach that I couldn't reach with just 3. That's fundamental. It is useful to have more than 3 primaries, but only because of this area here. Most of the stuff I could get to with 3. Suppose I had an infinite number. Suppose I was allowed to have as a primary every single color in the rainbow, every pure wavelength in the rainbow. Then what would be the shape of all the reproducible or the perceivable colors? What's that going to look like? Everyone's going kind of like this. A surface, yeah, the convex hull of the spectral locus is the technical term for it. So it'd be kind of, like this thingy. If this were a piece of chicken wire in 3-dimensional space, and we're buying that at Orchard Supply, and I kind of shrink-wrapped plastic over it, then that would be the shape. The convex hull of the spectral locus. And so this would be called the gamut of, let's call it the gamut of perceivable colors. Those are all the colors we can see, given any possible stimulus that lies within the visible spectrum, or any combinations thereof. Okay.
But it seems like even with 3, we can usually get to any given radial arc just with less intensity.
You mean what happens if we're out there?
Well, we can't get all the way out there.
Right.
We can get to something that the vector points that way from the origin, right?
Yeah, it'll turn out it's less saturation, actually.
Yeah.
It's a less pure wavelength. It'll look like an admixture of other stuff. We'll talk about that in a moment. All right, so here's what I just did. 3 cones, long, medium, and short wavelength, the stimulus, the response, and all right. So let me make one more drawing here. Suppose that we were missing one of our wavelengths, one of our receptor systems. Let's say we were missing our gamma receptor system. So what would we see? Suppose we were missing our gamma receptor system, what would the locus of spectral colors look like? Right, so everyone's kind of drawing it. It'd be a projection onto this plane. Every single point on the locus, every single point inside, if we were considering the whole gamut, would be sort of projected. These dotted lines that I just drew will be metamers then for a person who does not have that third receptor system. Take any point out here that's a mixture of wavelengths and that we see as a point in 3-dimensional space. That and all the other points along the line on the way back to whatever the projection of that is on this plane will be metamers to someone who does not have that gamma receptor system. That person's called a deuteranope. That is what color blindness is. So here are the percentages of males, and there are very small percentages of females in there as well, because it's a sex-linked trait. So this is a particularly hard set of, you have to, I have normal color vision, but I have to struggle actually to see the 37 here and the 49 here. But if you're a deuteranope, sorry, let's see, if you're a protanope, you won't see that. If you're a deuteranope, you won't see that. If you're a tritanope, you won't see that. These are hard. Anomaly means that you have a weaker system, or that the pigment is in slightly the wrong place there. Here's a more common one, these kind of diagrams. So there's a maze at left, which is recreated at right by strong red-green differences and subtle intensity differences. If you're a deuteranope, you'll see the maze like that. You'll see it very clearly because you'll see the subtle intensity differences and you won't at all see the confusing color differences. So the maze here will be as clear to you as it is here, if you're a deuteranope. And given the number of people out here, I imagine that there are some deuteranopes, or a couple. Okay, so I've already shown this, and I've shown this. So let's play some games here in this applet. So we've got this, and let's go up where we can see this. So there's a normal human, and let's make a deuteranope. Whoop. There. No more gamma, and you can see what happens here. Let's see, what else do we have? We have horses. They're deuteranopes as well. Let's do custom. Custom's kind of fun. And, let's reset it. Oops, no. And let's make custom. So edit row, and just for the fun of it, let's pretend that the row system, applet is so much fun to play with. Whoop, no. Oh, come on. That the row system looks kind of like the gamma system. So what would you expect to see over on the right? If I make the row system and the gamma system look the same. So kind of makes it a plane that sticks out at a 45-degree angle between the row gamma axes. I obviously haven't done it very carefully. Okay, that was fun. Let's try one more thing.
Is there any difference between that and a deuteranope?
Not effectively. It's a two-dimensional color space instead of a three-dimensional color space, like a deuteranope, just is in a different position in this space. But I drew something that probably doesn't exist in the natural world. All right, let's look at one more thing. Let's look at some cameras. So remember that a color camera has these filters. The filters are red, green, blue filters in a normal Bayer mosaic photographer's camera. So they each have spectral curves. So it's absorption in that case. It lets through a certain amount. So it is the transmittance case that I talked about earlier. And let's look at a Canon camera. So keep your eye on these sensitivity curves when I flick to a Canon camera. Makes a slightly funky, but it doesn't look too different than the human visual system. Go back to the human visual system. Let's try a Nikon camera. So that's kind of interesting. They're pretty similar to the human visual system. And indeed, they should be. Because if they were not, then there would be objects in the real world that we can discriminate that will look the same to each other in a photograph. We don't want that to happen. Or vice versa, there will be things that, what did I say, that look different? That will look the same in the real world, that will look different in a photograph. We don't want that to happen either. So we would like more or less the same set of metamers. Yes?
What about animals like a mantis shrimp that have more?
Yeah, so in going from a person with normal vision to a deuteranope, we made a projection onto a plane. So ducks, mallard ducks, or pentachromats, that's my favorite example of more than 3 visual systems. In order for a duck to experience what we see, you would have to remove 2 of its visual systems and project it from a 5-dimensional space down to a 3-dimensional space. And in so doing, there would be a lot of metamers. So things that the duck can discriminate that we cannot. That is absolutely true. We are not as good as a mallard duck. Okay. So here's where we are. We've looked at the metamerism in a camera and seen that we want to be roughly the same as the human visual system. Okay. Any questions on this? Let's see what the Dory says. It's beginning to get a little bit more complicated now as we think about these higher dimensional spaces. The way to think about it is, for every receptor system, there's another axis in this high dimensional space. And, but the spectrum, the incoming spectrum, is an infinite dimensional space, one for every wavelength. And the act of color vision is a projection from this infinite dimensional space down onto the n-dimensional space where you have n receptor systems. Either 5 for a mallard duck, or 3 for a human, or 2 for a dog, or 2 for a deuteranope human. Question?
Where is the trade-off? I mean, you might want to have many more receptors to see more colors. So is there like a trade-off happening somewhere?
A trade-off on the number of receptor systems? That's a good question. Maybe a question for an evolutionary biologist. So 3 was evidently useful to us. We could discriminate spectra, meaning combinations of wavelengths that we otherwise could not discriminate. And maybe that helped us avoid food poisoning, for example. But the duck evolved more. Maybe there are other things as a prey species that it cared about, or things that it ate. So I think it's a question for an evolutionary biologist. If you had 20 or 30 of them squeezing the cells that have those pigment into the retina could compromise resolution, for example. Maybe that's a trade-off. I'm guessing there. That's not a theory. Are there other organisms that have more than 5? There is this mantis shrimp, which has the number 13 sticks in my head, but they don't all overlap. It's 12. They don't all overlap. So the dimensionality of its color space may not be 12-dimensional. Okay. See, we're having fun here. Yeah?
Has the ability of camera lenses to produce those same curves gotten significantly better over time, or are we kind of topped out at this point? Like, 'cause it's still kind of a little bit wibbly and not quite the same.
Yeah, that's a good question, whether cameras have improved in their ability to match that. They don't necessarily want to exactly match it. They make trade-offs because having exactly those curves means less absorption and therefore less total sensitivity. And so there have been games that they played where they try to do different curves and then matrix afterwards, and we'll talk about that a little bit later, to trade off the spectral accuracy or the sensitivity against noise, signal-to-noise ratio.
But it's not like an area of hot competition between Canada and Nikon right now. They're both kind of below threshold.
Is it an area of hot competition? I do not know the answer to that.
Place where there's competition is trying to throw a fourth one.
Try to a fourth one,
Yeah.
especially a fourth one that might be clear and therefore be very sensitive. And so I showed that when I showed the mosaics.
Clear what? Sorry.
Clear meaning no filter at all, and therefore sensitive to all wavelengths, and therefore sensitive to lower light levels. You can also imagine, there's been talk recently about a red, blue, white, meaning red, blue, clear, which is a 3-dimensional color space. You can derive what you need from that by a matrixing of this space, but it's not going to have exactly the same spectral characteristics.
I mean, the human visual system has as well, right? So
You sort of have red, blue, green, white, right?
No, well, no, we don't have red, green, blue, white. The rods, maybe you're talking about, are only sensitive at very low light levels.
yeah.
So, yeah, so it doesn't really make a 4-dimensional color space except in a very narrow area called the mesoscopic vision.
They're also not white sensitive. White, they have a strong peak in the yellow-green.
Florian says that the rods have a strong peak in the yellow-green. Okay, reproducing colors using 3 primaries. Okay, this is going to get even messier. And what we'll do is let's go to a matching experiment. So this is a very clever experiment that Maxwell did. Yeah, the same Maxwell. He's all over the place. So what he did is he made two patches. So this is there are many versions of his experiment. His original version is a little bit different than this. I'll describe the version that I'm about to show you in the applet, which is a more modern version of the matching experiment. And on the right side, he would show, do it this way. On the left side, he would show a stimulus, which is a single pure wavelength from the rainbow, which you could easily make in the 1850s or early 60s with a prism and a slit. Okay? And he would present this to a viewer and then would present them with three other stimuli and give them knobs. And he could create those other three stimuli in a similar way with spots from a rainbow, or they could, in fact, be combinations of wavelengths. But let's make this simple, and let's say that they're each pure wavelengths. So we'll call this R, G, and B, although they're not necessarily red, green, and blue. They're just three wavelengths spread across the spectrum, and then let them adjust the relative amounts of each of them to try to match this. Can I have a volunteer from the audience? Someone with normal color vision, preferably? Surely. Some volunteer from the audience. Anyone? All right, come on up. Okay. Oh, look, Maxwell's matching experiment. Okay, I'm going to set the okay, 580 nanometers. You have to realize, of course, this is a bit of a simulation here. I don't have a prism. You're looking at this on a projector. Okay, go for it. Use my trackpad.
Turn off the curves.
What's that?
The curves are on.
Check the cheat button.
Yeah, there we go.
Sorry.
Otherwise it's a little easy.
He didn't see those. He didn't remember them anyway. All right, go for it. Right here on the trackpad, but you're looking up there. And those little triangles. There you go. Mm-hmm. Oh, 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 ooh. Okay, so we're not done with you yet. Here's the answer. There. Those were in the same ratio as he did. Okay, that was pretty easy. Let's try this one. Okay. How long should we let him suffer? Okay, so thank you very much. The answer is that you couldn't have gotten this. I deliberately chose that wavelength as being one that could not be matched by these other particular wavelengths that were chosen as the primaries. The answer is this. So let's look at that. Here's the answer. So let's look at that for a second. So as Maxwell did these experiments, he discovered, lo and behold, that some pure wavelengths could not be matched using any of the three that he came up with as the primaries. And so what he found it necessary to do in his experiment was to put 3 phantom knobs over here. And if you turned the first one, it would take a little bit of this wavelength and stick it over here and add it to the stimulus. Or this one, or this one. And that allowed him, and then that worked. And that's what's shown here. He had to, if this were Maxwell, he would have had to add a little bit of red to the stimulus in order to make a match using the other 2. And so he could represent this using a negative number. And so here are the curves. These are the results of Maxwell's matching experiment. And he came up with curves that look really just like that. It's a remarkable experiment done with very simple apparatus. And notice that it does go negative in some places. And so we can think about this already because we were looking at the 3-dimensional diagram, remember? And we had the locus of spectral colors. And then we said that if you had 2 wavelengths, never mind the third one, you could get anything on the line between that, but you couldn't get this. And so you could think about this as requiring a negative amount of this. In other words, you'd have to add a little bit of this, of this, you'd have to add a little bit of this primary to the other side in order to bring yourself out here. You'd have to desaturate the stimulus. And that's represented as the negative amounts here. Absolutely remarkable experiment, which then helped him understand the 3-dimensional nature of color space and how color mixing and primaries work. It's really a tour de force experiment and understanding. But it's Maxwell, so. All right, so here's what we just did. Some stimuli cannot be matched unless first desaturated by adding some of one primary to the stimulus. And that's represented by negative amounts of these functions, which are called R bar, G bar, and B bar. And the sequence of those make these things called the trichromatic matching functions, which you just looked at. Remember that they are for a particular set of primaries. If I change the primaries, if I move these around, those matching curves will look different. But for any 3 set of primaries that do a reasonable job of spanning all the colors we can see, there will be negative going stuff. There will be negative curves. And so we can think about this. So I did a crude drawing that looked kind of like that one that I had earlier, drawn better, but this time with these matching functions. So you've got an input spectrum, and you'd like to match it using a particular set of primaries. You will take the matching functions for those primaries and multiply them at each wavelength and integrate. And that's exactly the Young-Helmholtz-Maxwell trichromatic theory. And here are the formulas. At each wavelength, you multiply by R bar, G bar, and B bar, and integrate. Remember, that's for a particular choice of primaries. Choose a different set of primaries, either pure wavelengths or mixtures of wavelengths, and the matching functions will change. Okay, let's go back to the applet. Not this one. This one. And here is a version that has 3 primaries. Okay? And, oh, sure, let's show the tick marks. There. And on this version of the applet, we can show all mixtures of those particular primaries. So there's the triangle that we talked about before. And if we can include mixtures that have less than 1 or less than or equal to 1 as their total brightness, it'll be that tetrahedron back to the origin. But look what happens. Let me align, let me align the red and green axis. So not rho and gamma, but red and green. Whoops. And there it is. So I've aligned red and green. And notice the way this bows out. That bowing out means that in order to match those colors, I would need to put in a negative amount of that red primary, meaning I'd really have to add a little bit of the red primary to the others, to the stimulus. And that is exactly this stuff over here, in kind of the cyanish part of the spectrum where I would have to add a little bit of red to the stimulus in order to match it. And this bow over here is this bow over here, which is not all that visible in this particular scaling, and so on. Okay, people see how that works? Let's play some games here. Let me wait on the games. It'll be better in a minute. Okay. So that's what I've said. Responses, there's the gamut of reproducible colors for those particular set of primaries. Okay. Now let's go back to the applet. Let's go to the third one down here. And I've got some more stuff I can show you. So let's put on the tick marks, tick marks. And there's that. I like showing the gamut. All right, so I have chosen as my primaries here 3 pure wavelengths. And they're represented at the bottom. That's supposed to be a spike. So we can move them around. See what happens? So move around the red primary. The 3-dimensional diagram only updates every once in a while if I release the mouse. But you can see the way all the matching functions change if I move any one of the primaries, because they're all interrelated. All right, here's a fun game. Let's try editing one of these. Let's try replacing the red primary with something that has already within it a mixture of wavelengths. So what do you expect to happen on the 3-dimensional diagram on the right when I release the mouse? What's going to happen with the red primary axis on the right? Florian? It detached from the spectral locus because it's now itself a mixture of wavelengths and be further in. And there it is. Okay? Let's do the same to blue. Let's call it a mixture of wavelengths. Same thing for green. So these are practical primaries. Unless you happen to have a laser system, the primaries for a reproduction system like a color television will have spectra that are not pure wavelengths, and therefore they will have varying gamuts of reproducible colors that will not include all the rainbow colors. So a practical television set looks like this.
Which means that in some sense, the picture we're seeing is itself inside the actual...
You mean the picture you're seeing on the projector of the... Yes, of course. This whole thing is a simulation. Yes, that is absolutely true.
You're one step further inside the matrix.
Yeah. In other words, the colors that are being displayed here are even... Yes. I can make this even uglier. Let's take the green and make it a linear combination of blue and red. So what do you expect to happen on the right-hand side when I do this? I'm making one of them linearly dependent on the other two. I'm effectively going to reduce the dimensionality of my reproduction space here. And sure enough, I'll get sort of almost a planar figure. That's not a very good reproduction system. You wouldn't sell many TVs. Okay, do you begin to see how all this fits together? This is for a particular set of primaries. The matching functions also show this. Look, the red and the blue matching function look almost identical.
Is the ideal system the one where there's the least area under 0 for the matching functions? So that sort of shows you how much you can reproduce?
So that's a good question. Is the ideal system the one, here, let's reset this mess. Is the ideal system the one that has the least area under? My guess would be not, because there's other stuff going on, like total brightness and efficiency and things like that. And there may be certain colors that are preference to us. We're more sensitive in certain areas, flesh tones, greens. So I think that's probably a more complex, it's a good question, but it's probably a more complex question. All right. I don't know if that's the Dory or it's a really. It's a phone call to me, and I'm using a Google Voice number, so we'll ignore that.
Long time listener, first time caller.
Okay. All right. So,
Mark, there was a question.
yeah, sorry, question? Yeah.
What is the relationship between the response curves of the cones and the color matching function? Is there any relationship? And
Between the response function and the tristimulus?
yeah.
Yes, there is. The sensitivity curves you can think of as being independent, but once you've set a set of primaries, then you should be able to derive the matching functions from them. I can point you to a textbook that has those kinds of derivations. That's a good question. All right, so I've shown this. I've talked about this. You can clearly add a fourth primary here, and that would help. All right. Any more questions?
Could a matching function be never below 0?
Sorry, can a matching function,
Be always above 0?
could any one of the matching functions ever, I wouldn't think so, because around that point, even if this were out at the edge, unless you've got other primaries like right nearby it. No, let's see, is that the right answer?
By choosing the primaries cleverly.
It's provable that with 3 primaries you can never get.
Yeah, certainly with 3 primaries you can't. The question is if you had a lot of primaries. I think the answer is no, it's always going to have negative stuff, unless you have an infinite number of primaries. Unless you have primaries equal to the entire rainbow, there'll be negative stuff for something. Yeah?
Has anyone ever made a laser display system, kind of like you were alluding to?
Sure. Yeah, sure, you can make laser display systems, and they'll have great saturation. They'll still have negative going stuff, unless you've got a laser for every wavelength. Yeah. Sure, they'll have very saturated colors. Don't look into the laser.
So since you could get a larger gamut with a 4 primary system, why hasn't that been done more in, at least in screens?
Aren't there 4 primary? There are. There are displays that have 6. Yeah, sure. But as we'll talk about next time, the standard colors that we sense as well are kind of limited. And so given that gamut, there isn't a lot of commercial value in having a larger system. But certainly when people print with inks, they'll add another primary to get more saturation, one part of the spectrum. So let's switch. I want to make sure that we have time before we run out of time. This time to talk about the next big question, which is additive versus subtractive color mixing. Okay, so I'm going to completely mess up the production system here by trying to turn out the lights and show a little demo here with these guns. And I had trouble even finding a place where we could show it, so I'm going to try to show it on that wall. Oh, try it on the whiteboard. All right. Yeah, so I've got blue and red and green, okay? So all of you should know what happens when we mix the light of red and green. Been to the Exploratorium? Yeah, yellow, yeah. And if we mix this, we'll get some kind of magenta. And if we mix this, we'll get kind of a cyan. And I can't hold all three of them at once. We'll get white. All right, so you've all been to the Exploratorium. So that's additive. So if we have a cathode ray tube, that's what will happen. If we have dots on a newspaper and we're standing back, then they're kind of adding in our eye. That's what happens. But that isn't what happens when you add layered inks, one on top of another. And, so if we create that kind of a system, then it's a subtractive system. And in a subtractive system, it's like stacking these filters. And so the way to think about it is we'll take the red filter and we'll take the green filter, and there's a certain amount of light being reflected, or well, let's use one of these, going through here, and it'll go through the red filter and then through the green filter. And it'll be multiplied by the transmittance of each of these as it goes through. So what color do you expect to see when we do that? I've got the red and the green here.
Is there a narrowband?
He knows too much. All right, so let's try that. Here's the red and here's the green. Drum roll, please. So black. So that's not a very good printing system, huh? And the same thing would happen if I mixed some of the others. Yeah, so let's think about that. Maybe let's look at the applet. Come back to that in a moment. And let's switch that to that applet. So I've got this nice color mixing applet. So you can play with that. You can say, here's an additive system on the left. And we've got lasers, red, green, and blue. And here's the resulting color that we see. And so if I turn off one of them, here's yellow. So that's kind of fun to play with. And they could, instead of just being like that, they could equally well be broader, like that. And because there are an infinite number of spectral power distributions that create the same colors, those are metamers, we still get a white. If I turn off the blue, we still get a yellow. Yeah, there, pure yellow. Okay? Now let's talk about subtraction. So in subtraction, we start with a white source, let's say that light, and then we multiply. See the multiply symbol there? Multiply by the spectral transmittance of one, then the other, then the other. All right, so let me reproduce what we just did. And we got black. And in fact, I can even take away the blue by making it 100% transmissive. There. We still get black. And if you look at the spectral power distributions here, you can see why. So we started with white, light, and then it passed this part of the spectrum, but nothing else. And this passed this part of the spectrum, but nothing else. And so it ended up with black. Well, All right, you're thinking to yourself, yeah, I know that, but cyan, magenta, yellow are the right ones. If we're printing with inks, it's cyan, magenta, yellow. All right, let's switch to cyan, magenta, yellow. Uh-oh. Wait, what happened? Let's analyze. Let's turn off the magenta. So we'll make that 100% transmissive. Oh, I'm still getting black. I don't get a green. Why don't I get a green?
Totally off phase.
Because they're pretty narrow. They are cyan, magenta, yellow, but there are an infinite number of cyan, magentas, and yellows because of metamerism. So it has to be more than just cyan, magenta, yellow in order to work as a printing ink. They have to overlap. And I can create that overlap just like this, little hack. Hack, hello. Ugh. It's not, that's too much of a hack. All right, so further down in the applet, here are the broadband cyan, magenta, and yellow. And, broadband cyan, magenta, yellow. And now if I turn off the magenta, I'll get a beautiful green. And I can demonstrate that here again. Take just one of these. And I've got cyan, magenta, and yellow. They are broad spectrally. And I can take them, drum roll please. Okay, or we can do cyan, magenta, we'll get a nice blue. Or we can do magenta and yellow, and we'll get a very nice red. So that is how printing works. So let me summarize those results. Okay, so what did we do? We first added lights by adding their spectral wavelength by wavelength, and we did subtraction by multiplying their wavelengths, wavelength by wavelength. And we've already seen that narrow is best for multiplying. I'll turn the lights back on. So narrow is best when you're adding, because it'll get closer to the spectral locus. But wide is best when you're subtracting, because then you'll get the overlaps you need in order to get intermediate colors. So the particular spectra are flexible. The additive primaries don't need to be red, green, blue. You can move them around. They kind of want to be in the reddish, greenish, and bluish parts of the spectrum, or you won't get a full range of colors. And the subtractive primaries don't need to be cyan, magenta, and yellow. You can move them around too, so they kind of will appear different colors. But you want these to be narrow if you're adding. You want these to be broad. And you can also add additional primaries to either system. A typical one is to add a black to a subtractive system called CMYK, so that when you multiply them, you still get a deep black when you're done. So the additive mixing can be interpreted as an interpolation in color space, as we did before. But you cannot show subtractive mixing on that same diagram, the rho gamma beta diagram. It isn't going to be an interpolation because you're multiplying, you're not adding. Last slide, let me just point out how printing works. So printing is actually a combination of both of these, because you lay down little dots of ink in a halftone printing system, and the dots of ink layer one on top of the other and do subtractive within each dot, or overlapping dots. And so with CMY, they will overlap partially on the page, making patches of meta-primaries, which then include red, green, and blue, just as I showed with the filters. And then you have all those dots of all those primaries, and they all add in the eye when you hold the printed page far enough away from you. And so those overall effects are modeled by a set of equations called the Neugebauer equations. Oops, sorry. Called the Neugebauer equations, which we won't go into here. Okay, so we see how additive and subtractive mixing works. We'll pick up next time and we'll talk about the polar and cylindrical color spaces, and we'll talk about white balancing and gamut mapping and other practical applications to photography.